Well, hey there, guys. Mr. Carlson here. And for this part of our notes, we're going to be taking a look at periodic trends. So, the trends in how the sizes of atoms and the sizes of ions change as we move across the periodic table. We're also going to look at electronegativity and the trends that we see with that. So, let's start off right here. Atoms, if we move down the periodic table, so let's say we started in a group and we move down group 1, atoms get bigger. This is the first trend that we see. Atoms get bigger as we go down a group. Now, why would that be? In fact, let's come over here. And so if we got our periodic table right here, and let's say we're in group 1 and we're starting right up here at the top with hydrogen, and as we move down that group, going from hydrogen to lithium to sodium to potassium, the sizes of those atoms gets bigger every period that I go down until I get down to here and I'd be at the biggest one. What would be the reason, you think? What would be the reason for that? And the reason is right over here. If we look, every time we go down a period in the periodic table, we are adding another energy level to that atom. So for hydrogen, I've only got one energy level, right? 1s1, so just one energy level. With lithium, I would have two energy levels. With sodium, I would have 1, 2, 3 energy levels. And so as we move down, we're adding more energy levels, which is making those atoms bigger. So more shells of electrons. The other thing that we want to think about is there is a greater nuclear shielding. Shielding is a term that's used quite a bit in the AP chemistry world here. So shielding, we can think about like this. We've got these protons that are in the nucleus here, and they are pulling these negatively charged electrons in. That's what holds those electrons in here. It's pulling them closer and closer. Well, as I get bigger and bigger, I'm adding more and more electrons that shield or get in the way of these protons trying to pull these valence electrons in. So the more energy levels I have, there's more of these inner core electrons here that kind of shield or get in the way of these protons pulling these valence electrons in, which in turn makes these bigger than I would with these smaller ones that only have like 1 or 2 energy levels, where those valence electrons are a little closer to that nucleus, basically. So that's the trend we see for going down the periodic table. What about moving across the periodic table, so going from left to right? Well, the radius of atoms, or the size of those atoms, would decrease. So they get smaller as you go right. So from left to right across a period. And why is that? Well, if we think about this, if we look at lithium, beryllium, and boron, so actually let's come back to the periodic table here, and we look, here's lithium, beryllium, and boron. If I start moving across the period like this, notice that all of these elements here are in the same period. They're in period 2, which means all of these elements, the highest shell or electron shell is going to be energy level 2. And so I'm not adding energy levels as I move across like I was when I was moving down a period. Instead, what I'm doing is I'm adding more and more electrons to that second energy level as I move across. And so if we think about the size of lithium, beryllium, and boron, let's come back over here. Notice that they're getting smaller because what I'm doing is I have more of those protons in the middle, and so more of a pull on those valence electrons, pulling them in. Lithium's only got 3 protons. Boron has 5, and so boron has a greater effective nuclear charge to pull those electrons in. So what we're going to say is more protons means there is a greater, what's called effective nuclear charge. So those protons are positively charged. They're pulling on these negative electrons. And since these are all a second energy level, they're not any further away, well, these protons, if I get more of them, they have more of a pull on those electrons, and so it makes the atom actually a little bit smaller. And so if I were to come back here, if we were to keep going, carbon would be a little smaller than boron, nitrogen would be even smaller than carbon, and we would keep following that until we got to neon, because neon, out of this entire period here, out of period 2 at least, neon would have the most protons, and so would have the greatest pull, and so would probably be the smallest out of that period 2. All right, so moving down here, based on their position on the periodic table, place these 3 elements, aluminum, carbon, and silicon, in order of increasing atomic radius. So again, atomic radius just means like the size. So we want to put them in order of increasing atomic radius. If we were to look at where those are on the periodic table, here they are, aluminum, silicon, and carbon are right here. Well, we know the trends are that as we move down, they're getting bigger, but they're getting smaller as we move across. So if I think about, let's say, between carbon and silicon, let's say, which one of those two is going to be the bigger out of those? Well, I know that as I move down, I'm adding energy levels. So I know that silicon is probably going to be bigger than carbon. But what about aluminum and silicon? Which one's going to be bigger there? Well, I know that as I move across this way, aluminum is going to be a little bit bigger than silicon because silicon has one more proton. And so which one is going to be the smallest out of these? Well, probably carbon, because even though aluminum is a little bit more to the left here, carbon is up 1 here. So it's got 1 less energy level, and that has a greater effect on the size, how many energy levels you have. So carbon is probably going to be the smallest. Carbon's probably going to be the smallest. And then after that is going to be silicon. And then after that, the biggest one out of those 3 is most likely going to be aluminum. So that would be the trend that we'd see with those 3 elements. Let's talk about ionization energy now. Ionization energy is the energy that's required to remove an electron from an atom. So the amount of energy that's required to remove an electron from an atom. If we look here, we've got magnesium. And notice for this, it says magnesium, to get it to be Mg plus 1, meaning lose 1 electron. That would be known as the first ionization energy, so that first valence electron, basically. And notice that the ionization energy is 738. We can actually look down here. I think this is the same one right here. 738 kilojoules per mole. And then if I wanted to remove the second valence electron that I've got there, that would be the second ionization energy. And notice that it's 1,451 kilojoules per mole. And then notice once I get to the third one, if I wanted to remove 3 electrons, that third ionization energy, notice there's a star next to it because it is much greater. So it does increase from 738 to 1,451. But then once I get to the third electron, it jumps way up, takes way more energy. What would be the reason for that? And the reason is this: if we look, magnesium, which is in group 2, or if we were to write out the electron configuration for that, we would see that it has 2 valence electrons, right? And so those first 2 electrons are relatively easy, or at least relatively close in how much energy that it takes to remove. But then once those are gone, and I go to remove that next electron, that third electron, for magnesium at least, is one of the core electrons, or one of those inner electrons. You can see it right here, actually. So here's that first electron, goes away. Here's that second electron. As soon as that goes away, that shell goes away, and now I'm trying to remove one of these inner electrons, which is closer to the nucleus, and so these electrons are held onto way more tightly than the valence electrons, And so I would need way more energy to try to pull those ones away. So the large jump in ionization energy means that a core electron has been removed, whereas these would be those valence electrons. The thing to keep in mind, and I've already mentioned this a couple times, but the number of valence electrons, and this is something you should remember from regular chem, but the number of valence electrons is the same as the group number that we find it in the periodic table. And the number of energy levels that an atom has is equal to the period number. So if we come back to the periodic table, the group number here tells us how many outer shell or valence electrons that you have. So if we look at, and that's for the S block and the P block, S block and the P block. Transition metals are a little different. So we're just going to focus in on the S and P block here. But if I look, all these elements in group 17, they all have 7 valence electrons. All the elements in group 18 here have 8 valence electrons. 6 for group 16, 5 for group 15, 4 for group 14, 3 for group 13. Jumping over here, we've got 2 valence electrons for these guys and 1 valence electron for these guys. And then, so those are the group numbers. Group numbers are along the top. The period numbers, which run this way, so for the rows, that tells you how many energy levels. So if I am an element in period 3, that means the highest energy level that I go to is the 3rd energy level. All the elements in period 4, their highest energy level, their valence shell is energy level 4. So let's just keep that in mind as we're going through and doing these problems. Next one, we have an atom in the 3rd period, and it has the following ionization energies. So if I look, the first ionization energy is 496 kilojoules per mole. The second ionization energy is 4,560. So going from the first one to the second one is a pretty big jump. So I know that whatever this atom is, I know that it only has 1 valence electron, right? Because once I get to that second electron, there's a huge jump in that ionization energy. So I know whatever this is has to have 1 valence electron. And since the problem is telling me that it's in the 3rd period, let's come back over here. All of these elements here have 1 valence electron, we said. Here's the 3rd period. Right here is sodium, is what we're looking at. So this one has to be Na, has to be sodium. So the first ionization energy, the energy required to remove the first electron increases as atoms are smaller. And why is that? Because valence electrons are closer to the nucleus, so they're held onto more tightly, and it requires more energy to remove them. So as it's smaller, those valence electrons are getting closer and closer to the nucleus, and so that ionization energy is going to go up. In other words, it's going to be harder to remove those electrons. Which atom would you expect to have a higher first ionization energy? Hydrogen, lithium, or sodium? So if we think about this, we're looking at right here, hydrogen, lithium, and sodium. Now, they all have only 1 valence electron. The difference is how many energy levels they have, right? Hydrogen has 1, lithium has 2, and sodium has 3. So for sodium, its valence electron is the farthest away from its nucleus. Hydrogen, its valence electron is the closest. And so hydrogen is going to have a stronger hold on that valence electron than lithium is. And lithium is going to have a stronger hold on its valence electron than sodium is. So if we come back over here, which one's going to have the highest first ionization energy? In other words, which one's got the strongest hold on that valence electron? It's going to be hydrogen. And then lithium would be next, and then sodium, and then we could keep going down that row. And so we could explain why. Why? Because we'll say hydrogen's electron is closest to the nucleus. Which atom would you expect to have a higher first ionization energy? Lithium, beryllium, or boron? So we're coming up over here again. This time we're moving across this way. Which one's going to have a tighter hold on those electrons? So if we look, lithium to beryllium to boron, they're all in the second energy level, their valence electrons are. But the difference is, as we move across, we're going to add more and more protons, more of that attractive force. So boron is going to have, out of those three, boron is going to have the tightest hold on its valence electrons. So we could say that boron, and we'll say because boron has the most protons, therefore tighter hold, or therefore I will say stronger hold. On electrons. And so that's going to have the higher, out of those three, is going to have the higher ionization energy, or more energy is needed to pull those electrons away. All right, let's keep going. So ionization energy is always positive. Always positive because when we're removing electrons, it always requires energy to overcome the force of attraction. We'll say force of attraction to the nucleus. And that means, going back to our thermochemistry, that it's an endothermic. Endothermic, because it requires energy, takes to break. So it's an endothermic process if we want to remove those electrons from it. So we'd always have to add energy to it. All right, so let's talk about now the size of ions. So remember, ions are when we either gain or lose electrons. Cations, which remember are ions with a positive charge, they have lost an electron. When they lose electrons, there's less repulsion among those electrons in that valence shell, and so the atomic radius, we'll say, shrinks. So it gets smaller. So cations are always going to be smaller than the atom from which it was derived because they're losing electrons, there's less repulsion, and so they're able to get pulled closer to the nucleus. Anions, on the other hand, so remember, anions are ions with a negative charge. They have gained an electron. There is now more repulsions that happen because I've now got more negative charges, and so they kind of get pushed back from each other, and so the atomic radius actually increases. So an anion is always bigger. And it makes sense that if I add electrons to this, it's going to be a bigger size. If I take away electrons, it's going to be a smaller size. So that's the thing you want to remember when we're forming the ions. If it's positive, it's going to be smaller than what it originally was. If it's negative, it's going to be bigger than what it originally was. So let's look at this first problem right here. Which atom is the smallest? I've got O2 minus, Mg2 plus, F minus, and Na plus. Let's come and look at the periodic table here. So the first one was O2 minus. So here's oxygen. 2 minus, remember, is where it gains 2 electrons. So really we can think about this as going 1, 2. It's gained 2 electrons, so it gets right here. The other one was Mg2 plus. Here's Mg. 2 plus means it's lost 2 electrons. So 1, 2. So it actually has the same number of electrons as O2 minus. F minus, so right here, means it's gained electrons. So it also has the same number of electrons as O2 minus and Mg2 plus. And then what about Na plus? Here's Na. Plus 1 means it's lost an electron. So really it's just like neon as well. So all of these elements, or sorry, all of these ions, I should say, they all have the same number of valence electrons. And so we should point that out. They have the same number of electrons. But which one is going to be the smallest? Well, I know out of these, just looking at these four, that the ones that have the positive charge, here, are going to be smaller than the ones that have this minus charge, right? Because we just talked about it up here that as we get a positive charge, we're getting smaller. As we get a negative charge, we're increasing in size. So let's think about magnesium and sodium. Which one is going to be smaller out of those two, and why would that be? And let's come back to the periodic table here. I've got magnesium, I've got sodium. If they both, when they ionize, have the same number of electrons, they both have 10 electrons, which one is going to have the stronger pull on those electrons? And it's going to be magnesium because it's got more protons. And so magnesium would end up being the one that has the smallest out of those, would have to be Mg2 plus, because they all have 10 electrons, but Mg has the most protons. It has 12 protons, and so it has the greatest pull to pull those electrons in closer, and so that would have the smallest size. What about the trend in sizes of these? So I've got N3 minus, O2 minus, and F minus. So let's come back over here, and we're going to look at, what was it? Nitrogen, 3 minus, so 1, 2, 3. We've got O2 minus, 1, 2. And then we've got F minus 1. So again, same thing. They all have the same number of electrons. Which one is going to have the smaller size? It's going to be fluorine, because it's got the most out of those three. Fluorine has the most protons, and so it's going to have the most pull on those electrons to pull them in closer. So F minus would have the smallest size. And for our explanation, we could say, we'll say all have 10 electrons, but F minus has the most protons to pull electrons closer in to make it a smaller size. All right, let's keep going. So now we're going to talk about electron affinity. Electron affinity is basically how much an atom likes electrons, and it's the energy that's required to add the first electron. So this is the exact opposite of ionization energy. Ionization energy was talking about how do we get rid of one. Electron affinity is looking at how do we add an electron to something. So electron affinity is hold on, I gotta find my place here. Electron affinity is usually negative, because energy is released when an atom receives an electron. So this would be an exothermic. So again, the exact opposite of ionization energy. It's an exothermic process. So the higher the negative values, that indicates a greater electron affinity. We can think about it as like more of a relief to the atom. So it's giving off more energy. If it's got those higher negative values, it's giving off more energy, becoming more stable. So if you've got a higher negative value, that means you have a really great electron affinity. Noble gases, noble gases have positive. They actually have positive electron affinity. Their affinity values are large, meaning that it would actually require energy to add an electron to these. The alkali metals are actually another example of this, because the noble gases in the alkali metals, they would way much rather get rid of electrons, as we're going to find out. And so it would actually require energy for us to try to add electrons to either the noble gases or the alkali metals. The alkali metals want to get rid of electrons, and noble gases are already very stable with the electron configuration that they have. So they don't want to lose electrons, and they don't want to gain electrons. They are where they want to be, and so that's why their affinity values would be positive, because it would actually require energy for us to try to add electrons to that. Electron affinity is highest with non-metals and lowest with metals. So as we're going to find out, non-metals really want to, for the most part, really want to gain electrons, and then metals actually want to lose electrons for the most part. So the higher the ionization energy, the lower the electron affinity. So let's take a look at this practice problem. Which atom would you expect to have the higher electron affinity? Boron, beryllium, or lithium? And out of those choices, it would actually be boron, because if we were to look at the periodic table, boron is the furthest this way. In other words, it's the most, we can think of, it's the most non-metallic. Boron, we'll say it is the most non-metallic, put that in quotes, non-metallic element. Out of these three, at least, it's the most non-metallic. It's not the most non-metallic on the periodic table, but out of these three choices, it's the most non-metallic. Or we could say it's further to the right. Further to the right. And since these non-metals over here are going to have the higher electron affinity, the closer we get to this side, the higher that electron affinity. The further we get this way, the less that electron affinity. Whoops, I keep going back to the wrong screen. So that brings us to this thing right here, electronegativity. So electronegativity is basically a measure of how strongly certain atoms will attract electrons to them. This is a non-measured value. So this is just values that are man-made that we place on electrons. So we basically take a look at these different elements. We see how well they are, or how good they are at taking electrons from things. And the better they are, the higher this electronegativity value. So really high electronegativity values means that you've got a really strong attraction for electrons and you're really good at taking them. If you have a low electronegativity, that means you're not at all good at stealing electrons. And so it is based on ionization energy and these electron affinity values. The element with the highest electronegativity is going to be fluorine. That is the most electronegative element on the periodic table because it's small. It's one of the smallest ones here, and so it only has 2 energy levels, and so its nucleus is really close to those valence electrons, and it's got the most out of this row here. It has the most protons, and so it's got a lot of pulling power. So fluorine, because of its size and how many protons that it has the highest electronegativity. It is really good at taking electrons from things, and that's also what makes it really reactive. That's what makes most of these, if you notice most of these halogens here, they have relatively high electronegativities, and the reason is because of where they are on the periodic table. So let's go to this last one here. Actually, let's go back 1 second because I just want to. So the trend for electronegativity. So let's write that right here. Electronegativity trends. So we're going to say that electronegativity increases from left to right. From left to right across the periodic table. So as I move from left and I go this way, those electronegativity values increase, and then those electronegativity values actually decrease as I move from top to bottom. So decrease from top to bottom. So fluorine would be the most electronegative, and then whatever element is in this bottom corner down here would be the least electronegative. Okay, so those are the trends you want to keep in mind with electronegativity. All right, so this very last one here. Noble gases have no electronegativity. So remember that noble gases, as we've said over and over again, are already stable, and so they do not need to bond. So don't need to bond. Or we'll say don't need any electrons. They don't need to take any electrons. They don't need to give any electrons away because they're already stable. So that's why they don't have any electronegativity values. Halogens, which would be things like fluorine, chlorine, again, these right here are the halogens, fluorine, chlorine, bromine, iodine. They have the greatest electronegativity because they only need one electron. It's all they need is just one valence electron to become like the noble gases, and so that's why they're very reactive and have a higher electronegativity. Metals have the least electronegativity, the lowest, because they don't want to gain electrons. They need to lose electrons. So that's why their electronegativity values are so low. They don't need to gain electrons. They need to lose electrons instead. And fluorine is the most electronegative element. We kind of already talked about that. It has to do that it's got the small size. We'll say small size, meaning greater attractive force for valence electrons. So which would be more electronegative, chlorine or sulfur, based on where they are in the periodic table? Let's come over here. We've got chlorine right here. We've got sulfur. The trend is as we move from left to right, they're going to get more and more electronegative. So chlorine would have to be the most electronegative out of those two choices.